Hello, this is an extra video this week for a review of the greens function. During review 2, I noticed that quite some people had some troubles with the greens function. And after noticing that, I noticed that that stemmed by the fact that I made a mistake in the mockup of review 2 that was very similar to the review 2 itself. So I would like to backtrace a little bit and have a little bit of a talk about Green's function, in particular in the case of Laplace equations. Laplace transforms, sorry. So let's look at the Green's function for the Laplace transform. So we have an ODE, an nth order ODE, that we can write as a linear differential operator of order n applied to y equal to a non-homogeneous term on the right-hand side. And we're expecting y to be a function of x or t going from 0 to infinity, and y takes real values. Because we want to use the Laplace transform, what we're imposing are boundary conditions at 0, imposing some conditions on y and its derivatives. So if L is a differential operator of order n, capital N, then we're imposing n-1 conditions on y, y prime, y second, and so on, up to y at the n-1th derivative of y. If we have something like this, we solve it with the Laplace transform method. So the Laplace transform method takes 3 steps. We see 2 in this first slide and the next one in the next one. We find the homogeneous solution. And to do that, we're solving our linear differential operator applied to y equals to 0. So we replaced the right-hand side with 0, but we're taking all the non-trivial boundary conditions. So we have all the y at 0 equals to y0, y prime equals to y1, and so forth. We're keeping all of them and solving this. Usually we will use the characteristic polynomial method. Once we have that, we put it aside and we solve for the particular solution. And for this, we use the Laplace transform. We use the Laplace transform of the linear operator applied to y, and this is equal to the Laplace transform of w. Then we solve for the Laplace transform of capital Y, and then we take the inverse Laplace transform. And we solve this while keeping in mind that all the boundary conditions are now trivial. So we don't need to keep that in mind. This makes our job easier. It's not necessary. We can merge these two situations by using the Laplace transform method with non-trivial boundary conditions, but it does become way more convoluted. So I would, and when I do solve things, I do keep them separate. First solve the homogeneous solution and then the particular solution with the Laplace method. Now that we have both of them, we sum the two. When we're using the Green's function, what we want to do is writing the particular solution as a convolution between the Green's function and the right-hand side. And then we can again write y, the full solution, as the sum of the homogeneous solution and the partial solution, particular solution. But this is one of the mistakes I noticed in the review too. The Green's function does not include the homogeneous solution. The Green's function only works to fix the particular solution. So how do you compute the Green's function? So G solves our differential operator applied to y equals to delta x minus tau. Let's try to be more precise by working through an example. So we have y second plus 5y equals wx, and we have a boundary condition at 0 for y and the boundary condition at 0 for y prime. So the homogeneous solution solves y prime plus 5y equals to 0 with the non-trivial boundary conditions. So y0 equals y0 and y prime 0 equals y1. So we write that the homogeneous solution y0, depending on x, is the sum of two exponentials with coefficients in front that depend on the boundary conditions and exponents that depend on a characteristic equation. Then the particular solution solves y second plus 5y, so our linear differential operator, equals to wx with trivial boundary conditions. So y0 equals 0 and y prime 0 equals 0. And we can approach it in two ways. We can either straightforwardly go for fixing y. So we have that s second capital Y, where capital Y is the Laplace transform of small y, plus 5 capital Y equals the Laplace transform of w. Then we solve this by saying that capital Y is the Laplace transform of w divided s squared plus 5. And because of the properties of the Laplace transform and the convolution, then the particular solution is equal to w convoluted L inverse 1 over s squared plus 5, where we used that the inverse of the Laplace transform of w is just w itself. And here, this L inverse of 1 over s squared plus 5 is the Green's function. But I can also determine it by saying that the Green's function is a function of x and tau, such that it solves the linear operator equals to a right-hand side that is the Dirac's delta computed at x minus tau, and the trivial boundary conditions. Then we retrieve, following the same steps as we did before, that the Green's function is equal to the Dirac's delta computed at x minus tau convoluted L inverse 1 over s squared plus 5. Here tau is arbitrary. So if we compute this convolution, well, the convolution of something times delta computed at x minus tau is just that something computed at x minus tau. So the Green's function, g, if we consider it as a function of x and tau, is the Laplace inverse of 1 over s squared plus 5 computed at x minus tau. So everywhere in our function, in the writing down of the Green's function, we always have this block x minus tau. We never have x on its own, we never have tau on its own, we always have this constituent block x minus tau. And we can just say that the Green's function computed at x minus tau is this value. So we started by saying that the Green's function is a function of x and tau. And now we say that it's actually a function of just x minus tau because it appears all the time in this block. Now we can compare the two approaches by saying that from the Green's function approach, our partial solution is the convolution of w and g, the Green's function that we just constructed. This is the integral from 0 to x of w computed at theta times g x minus tau. Sorry, I said theta. I meant tau. So integral from 0 to x of w computed at tau times g computed at x minus tau, d tau. And now we check it again, and we replace the Green's function by what we just computed. So the inverse Laplace transform of 1 over s squared plus 5. So we have that our equation is the particular solution. It's the integral from 0 to x of w computed at tau times the inverse Laplace transform of 1 over s squared plus 5 computed at x minus tau d tau. And this is the same as saying that it's w convoluted the inverse Laplace transform of 1 over s squared plus 5. So the two approaches correspond. If we want to use the Green's function to compute the full solution of the problem, we have to use it first to compute the particular solution and then sum the particular solution to the homogeneous solution.